What's up guys, this is Massey. Welcome to another video. In this video I want to talk about second order rate law, and then I want to talk about half-life time as well and see different questions. So when we consider a general reaction like A of A gives products, A is the coefficient and the capital A is the compound, it results in some products. How do we figure out we are dealing with second order rate law? We can say that rate equals to negative delta A divided by delta T equals to K times A to the power of 2. So it means that rate of change of concentration of reactant with respect to time is equal to K times concentration of A to the power of 2. So in general form we have K times A to the power of n. When this n equals to 1 is going to be first order, when n equals to 0 is going to be 0 order, and in this case n equals to 2, which means that it's second order. K is called rate constant and it is depending on temperature, and A is the molar concentration of reactant to the power of 2. So rate of change with respect to time, and we have negative because we know the concentration of reactant is decreasing over time, so we need to multiply it by negative to make it positive value. So the integrated second order rate law is gonna be like that. How do we end up having this reaction? I'm gonna write it for you right now in a piece of paper. We need to integrate it. It says negative delta A over delta T equals to K. If you want to write it in terms of differential form, dA over dt, K A to the power of 2. Then I bring A squared in here and move delta T over there. Then we need to integrate it from 0 to 4. 0 means start of the reaction. T can be any time. So start of the reaction, the concentration is A naught, and the final one is going to be A. So when you find out the reaction, the integration of negative dA over A squared is going to be 1 over A. From A to A naught, and KT from T 0. So it's going to be 1 over A minus 1 over A naught equals to KT. That's going to be the integrated form. And we can also move this part to the right hand side. So 1 over concentration of A equals to K times T plus 1 over initial concentration of A. So that's the final concentration of A equals to K times T plus 1 over A naught. So now if you compare it with the equation of line, and when you graph 1 over concentration of A versus time, if you are dealing with the second order reaction, you're gonna end up having a line, and in that case slope is gonna be equal to K, and the y-intercept is gonna be equal to 1 over initial concentration of the reactant. So again, when you graph 1 over A, 1 over concentration versus time, and you end up having a straight line, it means that you are dealing with a second order reaction, and the slope is going to be equal to K, which is the rate constant, and y-intercept is going to be 1 over initial concentration of A. So let's go back to the original note. So we end up having this integrated form of second order reaction. Now we need to have two notes in here. One of them, a plot of 1 over A versus time will produce a straight line with slope equals to K. We just saw it. And the second one is going to be half-life time. Half-life time is going to be the time that concentration reduced to half of original concentration. So A equals to half of the original concentration. If we sub it in the original integrated form, it's going to be 1 over A naught divided by 2 equals to K times T half, which is half-life time, plus 1 over A naught. When you rearrange it, it's going to be 2 over A naught minus 1 over A naught equals to K times T half. And then that's going to be 1 over A naught equals to K T half. So T half is going to be 1 over K and initial concentration. That's how you find out the half-life time for second order reaction. So let's see some examples now. So it says butadiene reacts to form its dimer according to the equation 2C4H6 gives C8H12. The following data were collected for this reaction and a given temperature. So these are concentration of butadiene, and here we have time. It says, is this reaction first order or second order? So what does that mean? It means that we need to have time with respect to 1 over concentration of butadiene. If you end up having the linear relationship, it means that we are dealing with a second order reaction. On the other hand, we can find ln C4H6. It means that you convert the concentration into ln concentration. If you have the linear relationship between these two, it means that you are dealing with a first order reaction. We already had a video regarding first order reaction. I will leave it in the description in case you want to review that. So I need to write the time in here: 0, 1000, 1800, 2800, 3600, 4400, 5200, 6200. Then I need to write the concentration. I need to calculate the inverse of this concentration. So that will be 0.01 is going to be 100. Then we have 160. Then we have 210. Then we have 270, 320, 370, 415, and 481. So these are going to be the inverse concentration. Now ln concentration is going to be negative 4.605, negative 5.075, negative 5.348, negative 5.599, negative 5.767, negative 5.915, negative 6.028, negative 6.175. So now we need to graph these two, and we need to graph this to see which one shows you a linear relationship. So first of all, I'm gonna graph this ln concentration versus time. If you do it, ln of C4H6 with respect to time, you're gonna end up having something like that. If you do it 1 over C4H6, you're gonna end up having a straight line like this. So it means that since the inverse of concentration gives you a linear relationship, it means that you are dealing with a second order reaction. So we are dealing with a second order reaction. That's the answer to the part A. Let's see the part B of this question. So as you see, part B, it says, what is the value of the rate constant? It means that what's the value of K? How do we find K? K must be the equals to the slope, because we already said the integrated form is KT plus 1 over A naught, and the slope must be equal to the K. So slope is gonna be change in y divided by change in x. So it is rise over run. So what we can do, I'm gonna consider the first and last in here. So it's gonna be 481 minus 100 divided by 6200 minus 0. That's gonna be 381 divided by 6200. That's gonna be 0.0614. So that's gonna be 6.14 times 10 to the power of negative 2 liter per mole per second. That's the unit for rate constant for second order reaction, liter per mole per second, or you can write it in terms of liter mole to the power of negative 1 second to the power of negative 1. Sometimes you have it in terms of minute, sometimes you have it in terms of hours, but seconds and minutes are more common. Why do we have this kind of unit? Because here rate equals to K times concentration to the power of 2. The rate is always mole per liter per second, or mole per liter per time. If we consider second for now, it's going to be mole squared over liter squared. So K will be mole per liter per second, mole squared, liter squared. So that's going to be liter per mole per second. So that's going to be the unit for rate constant, and we already calculated the value in here. Now part C. It says what is the half-life, and I already showed you the equation for finding the half-life of the second order, which is totally different from second order and zero order. It is T half equals to 1 over K times initial concentration. So that's gonna be 1 over 6.14 times 10 to the power of negative 2 times initial concentration. 10 to the power of negative 2, which is the initial concentration, as we had it here, times 0 is 0.01, which is 10 to the power of negative 2. So time is going to be 1.63 times 10 to the power of 3 seconds, or 1630 seconds. Both of them are the same thing. So that's the half-life time. Let's see another example. So in this example, the rate of the reaction NO2 plus CO gives NO plus CO2 depends only on the concentration of nitrogen dioxide, which is NO2, below 225 degrees Celsius. At a temperature below 225 degrees, the following data were collected. Here we have time, and here we have concentration. As you see here, the concentration is reducing over time. It says determine the rate law, the integrated rate law, and the value of the rate constant. Calculate the concentration of NO2 at 2.7 times 10 to the power of 4 seconds after the start of the reaction. So as you see here, it didn't mention if it's a first order, second order, zero order. It means that we need to find out the order of this reaction, because it says determine the rate law. So what I need to do here, I'm gonna have time in terms of seconds, concentration of NO2 in terms of mole per liter, ln NO2, and here 1 over concentration of NO2. So that's 1.2 times 10 to the power of 3. Here we have 0.500. Ln NO2 is negative 0.693, and 1 over NO2 is 2. Next one is going to be 3.00 times 10 to the power of 3, 0.444, negative 0.812, 2.25. Here we have 4.50 times 10 to the power of 3, 0.381, negative 0.965, 2.62. 9.00 times 10 to the power of 3, 0.25, negative 1.386, 4. Here we have 1.8 times 10 to the power of 4, 0.174, negative 1.749, 5.75. So now if you graph it, you can then double check the numbers later on for possible mistakes. So we have ln NO2 versus time. That's gonna be something like this. And if you graph 1 over NO2, it's gonna be something like this, which is a straight line. So the plot of 1 over NO2, the concentration of NO2 versus time, is linear, so the reaction is second order in NO2. So the rate is gonna be K times NO2 to the power of 2. And there is gonna be 1 over A equals to KT plus 1 over A naught. Instead of A, you can put NO2. For simplicity, I just show it as A. So, what else it asks us to find? We need to find out the rate constant. So the rate constant is going to be K, which is going to be rise over run. That's going to be 5.75 minus 2. 1.8 times 10 to the power of 4 minus 0. That's going to be 2.08 times 10 to the power of negative 4. And as we saw earlier, the unit is going to be liter over mole over seconds. Or again, liter, mole per to the power of negative 1, seconds to the power of negative 1. Now we have the K value. It says that calculate the concentration of NO2 at time 2.7 times 10 to the power of 4 seconds after the start of reaction. So I'm going to say 1 over A equals to KT plus 1 over A naught. So now we have the initial concentration. So this one is given. We have K. The time is given, so we can find out the final concentration. So 1 over A equals to K, which is 2.08 times 10 to the power of negative 4, times time, 2.7 times 10 to the power of 4, plus 1 over A naught. A naught is the initial concentration, which is 0.5. So when you calculate it, 1 over A is going to be 2.08 times 10 to the power of negative 4 times 2.7 times 10 to the power of 4. That's going to be 5.1. It's going to be 7.62. That's 1 over A. So A will be 1 over 7.62, which is going to be equal to 0.131 molar or mole per liter. So that's how we find out the concentration at any time. Let's see another example. A certain reaction has the following general form: A of A gives B of B at a particular temperature and initial concentration of 2.8 times 10 to the power of negative 3 molar concentration versus time. Data were collected for the reaction, and the plot of 1 over A versus time resulted in a straight line with the slope value of 3.6 times 10 to the power of negative 2 liter per mole per second. Determine the rate law, the integrated rate law, and the value of the rate constant for this reaction. Calculate the half-life for this reaction and how much time is required for the reaction for the concentration of A to decrease to 7 times 10 to the power of negative 4 molar. So here it says a plot of 1 over A versus time resulted in a straight line. It means that we are dealing with a second order reaction, and the slope is 3.6 times 10 to the power of negative 2, which means that K is 3.6 times 10 to the power of negative 2, as we saw it earlier. So rate is going to be K times A to the power of 2. So that's how we write it. And the integrated form is going to be 1 over A equals to KT plus 1 over A naught. So far we know the value of K and we know the initial concentration. So that's it for the first part. Second part, it says calculate the half-life. The half-life of the second order reaction is going to be T half equals to 1 over K, which is 3.6 times 10 to the power of negative 2. Initial concentration, which is 2.8 times 10 to the power of negative 3. That will be 9,920 seconds, which is going to be around 2 hours and 75. So that's going to be the half-life. And in part C, it says how much time is required for the concentration of A to decrease to 7 times 10 to the power of negative 4. So we sub it in this formula. 1 over 7 times 10 to the power of negative 4 equals to K, which is 3.6 times 10 to the power of negative 2 times time plus 1 over initial concentration, which is 2.8 times 10 to the power of negative 3. So 1428.57 minus this number, 1 divided by 2.8 times 10 to the power of negative 3, 357.14. 1071.43 equals to 3.6 times 10 to the power of negative 2 time. So time will be 29,761, or 62 if you round it, seconds. So that's going to be the time it takes in order to concentration to be dropped to 7 times 10 to the power of negative 4. Let's see another example. It says iodine atoms combine to form molecular iodine in a gas phase. I plus I gives I2. The reaction follows second order kinetics and has the high rate constant of 7 times 10 to the power of 9 per molar per second at 23 degrees. If the initial concentration of I was 0.086 molar, calculate the concentration after 2 minutes. Calculate the half-life of this reaction if the initial concentration is 0.6 and if it is 0.42. First of all, I need to mention the unit in here. As you saw here, the unit for K is going to be liter per mole per second. And as you know, mole per liter, it is shown by capital M. So liter per mole, as you see it here, is going to be m to the power of negative 1. So instead of L over mole per second, or L mole per to the power of -1, S to the power of -1. You can say molar to the power of -1, S to the power of -1, or also 1 over M and over S. So all of them are correct. So it says if the initial concentration of 0.086, calculate the concentration after 2 minutes. So the rate constant is given. We can say that 1 over A equals to KT plus 1 over A naught. So 1 over A, K is 7 times 10 to the power of 9. 2 minutes. Since it's in terms of seconds, we need to convert it to seconds. So 2 minutes is going to be 120 seconds plus 1 over initial concentration, which is 0.086. So 7 times 10 to the power of 9 times 120 plus 1 divided by 0.086. That's going to be 8. That's going to be 8.4 times 10 to the power of 11. And you need to inverse it. So A will be 1.2 times 10 to the power of -12 mole per liter, or molar. So as you see here, after 2 minutes it dropped significantly. Why? Because K is really high. And it also mentioned that has the high rate constant. It means that the rate of reaction is really high. So that's the answer to part A. B, it says calculate the half-life of the reaction for initial concentration of 0.6 and if it is 0.42. So T half is going to be 1 over K. K is 7 times 10 to the power of 9. 0.6. And another time is going to be 1 over 7 times 10 to the power of 9. 0.42. That's going to be 2.38 times 10 to the power of -10 seconds. And here you have 3.4 times 10 to the power of -10 seconds. That's the half-life time, which is extremely small. Again, because the reaction rate is really high. So in this example, it says the rate constant for the second order reaction, 2NOBr gives 2NO plus Br2, is 0.8 per molar per second at 10 degrees. Starting with the concentration of 0.086 molar, calculate the concentration of NOBr after 22 seconds. So again, we need to write the integrated form. K is given, which is 0.8. Time is given, 22 seconds. Initial concentration, which is given, 0.086. So that's going to be 0.8 times 22, that's 17.6 plus 1 divided by 0.086, that's going to be 11.63. That's going to be 29.23. And you need to flip it. 1 divided by 29.23 is going to be 0.0342 molar. So that's going to be the concentration of NOBr after 22 seconds. Let's do the part B. It says calculate the half-lives when the concentration is 0.072 and when the concentration is 0.054. So T half equals to 1 over K initial concentration. K is 0.8, 0.072, and for the second time it's going to be 1 over 0.8, 0.054, because we need to find out the half-life time for two different initial concentration. That's going to be 17.36. It's going to be 23.15 seconds. So it means that for larger initial concentration, we have smaller half-life time, which makes sense because the initial concentration is in denominator. Let's see one more example. The rate constant for the second order reaction of 2NO2 gives 2NO plus O2 is 0.54. 0.54 molar to the power of -1 s to the power of -1 at 300 degrees. Again, as you see here, always the reaction constant is given at the specific time because K is changing with time. For larger values of temperature, you usually get the larger value for K. How long in seconds would it take for the concentration of NO2 to decrease from 0.62 to 0.28? So we need to use the integrated form again because it mentioned that it's second order. Otherwise, we need to use another formula. So 1 over final concentration, which is 0.28, equals to K, 0.54, times T plus 1 divided by 0.62. So 1 divided by 0.28, that's going to be 3.57, 0.54, T plus 1 divided by 0.62, 1.613. So that's going to be 0.54 T, 3.57 minus 1.613. It's going to be 1.957. So T is going to be 1.957 divided by 0.54. That's going to be 3.62 seconds. So in 3.62 seconds, the concentration is going to drop from 0.62 molar to 0.28 molar. So that's how do we deal with this second order reaction and how to find out the half-life time for second order reaction. I hope you enjoyed this video. Please leave me a comment if you have any question, and please don't forget to subscribe this channel. You can have access to many other videos regarding chemistry, physics, and math. Thank you for watching and have a great day.